Perfect. Welcome, guys, to episode, I think, 92 of Accents from Trial. And as always, let me know if you guys can hear me okay in the comment section. And today we're going to be talking about dark matter. And I'm just going to get started right away. My guest today is Pavel Kroupa. I hope I pronounced that right. I already forgot. I'm really bad with names, but I'm going to bring him right in. And let's see. There we go.
Hello.
Hello. Thank you. Thank you so much for coming. So yeah, if you tell a little bit about yourself to the audience, what do you do and what your research is in?
Yeah, so maybe just a little bit of the background. I was born in Czechoslovakia, a country which doesn't exist anymore. I went to school in Germany and South Africa and got my degree in physics at the University of Western Australia and the PhD in the University of Cambridge in England. And my habilitation in the University of Kiel in Northern Germany. And since 2004, I'm a professor at Bonn University, and I'm also now a professor at Charles University in Prague. So I'm working with a research group which is very international in Bonn and in Prague. And we've been studying this problem, so the properties of galaxies, and increasingly cosmology since 25 years.
Gotcha. Perfect. Thank you so much. So I guess the first question I'll ask you is, what even is dark matter? Like, how is that defined? How do people talk about it?
Yes, well, dark matter is, you could say, the greatest problem in physics today. It's a very serious problem. And the reason why the overwhelming number of colleagues of physicists and astronomers are convinced there is dark matter is because when we observe the motions of objects in the sky, but in very far away regions, so in the outer regions of our galaxy as well as in other galaxies, the objects are not moving according to what we would expect if we apply the laws we know from our solar system or from Earth. Okay, so that's basically, if we think that the law of gravitation is universal according to Newton, we are in the non-relativistic regime always, so Newton, then this law fails in those regions, in galaxies, basically. And it can be maybe fixed by postulating that there's more matter which pulls stuff together. So the galaxy is rotating too rapidly. It would fly apart. So you need to put in extra glue, you could say, extra matter, which pulls more and therefore keeps it together. And this matter can't be seen, cannot be detected, and so it's termed dark matter in the sense that it doesn't at all interact with normal matter via photons, via light. It's a bit like neutrinos, which also pass through us without noticing. They are a normal part of matter, so they are well understood these days, or quite well understood. This form of dark matter, dark matter is maybe more an extreme form of neutrino-like, you could say, because it basically doesn't interact at all. So it just passes through everything, and we can't detect it. Only if you have a large amount of it, then it starts to gravitate. As an individual dark matter particle can be extremely low mass, or it could even be a little black hole. We don't know.
Right. So, just going to post that real quick. I'm a layman, so I apologize if I am confused here. But my understanding was that Newtonian physics is in some sense outdated, right? Like Einstein's work I thought, did away with some of the previous incarnations of physics. Am I right about that?
Well, that's true. That is absolutely my understanding of the physical reality. Outdated in the sense that it's not the fault of Newton or Einstein, of course, but it's important to realize the way these laws were derived. So Isaac Newton was incredibly brilliant, right?
Sure, of course.
Yeah. So one has to imagine that there's this young person, he was in Cambridge, thinking about matters, then he knows the moon's going around the earth, and he sees an apple forming. That's the general story, but that's probably actually what happened. So he watched an apple forming, and how these things happen. A thought crossed his mind, and he thought, well, if the apple is falling to earth and the moon is going around the earth, it seems that the earth is attracting both, right? And so he postulated this as a conjecture, and then went on to develop a theory which actually accounts for this. And you have to imagine that he did this at a time when the mathematics didn't exist.
Right.
Nobody knew how to do these calculations, right? So he actually invented the mathematical tools to do these calculations, and derived from the law of the motion of the moon, the falling apple, and the motion of the planets, his universal law of gravitation. It's one of the greatest intellectual feats ever achieved in humanity. And that stood the test of time until Einstein. That was, before 1916, he developed his theory of general relativity. So he reformulated the same law, this just with a different mathematical way, and by conjecturing again that the motion, so the laws of the gravitation is just it's not a real force. It's just what appears because space gets curved through the matter, right?
Right.
So he reformulated this in terms of curvature. So if you have a flat table, you put a ball on it. Of course, it doesn't do anything. If it's inclined, it will just roll down. But if it has dips and hills, then it will have a complicated path, right? So it follows basically the path it's easiest for itself to follow, and that's the same with the sun in the galaxy. It's moving around in this curved space and just seeking that path which is the best for it. I mean, that's the way one can calculate it precisely. It's a bit like optics, but this is what happens. And Einstein reformulated this, but under the condition that his new formulation must agree with Newtonian in the very small velocity regime, because we are in the realm of small velocities. All our aeroplanes, cars are moving with very small velocities compared to the speed of light, right? So in that regime, his mathematical formulation had to be the same as Newtonian, and that's where it fails. I mean, he managed to derive a correct theory, but mathematical formulation, but it's only valid for the solar system, and it's an empirical law. What then physicists and astronomers have done is they've taken this law and extrapolated it to many orders of magnitude. That's like a factor of 10, a factor of 10, a factor of 10 further away from the solar system. And they think that it should apply in galaxies, but it's an empirical law, so a law which you obtain from measurements, and that would fail usually. I mean, every physicist in kindergarten learns that you cannot extrapolate that amount, yeah? And right. You can, but most likely it will fail, and that's exactly what's happening. The law of gravity fails in the extrapolation, and the way it's one possibility is to postulate there is additional matter. Another possibility is to say that the law is actually different.
Right, and as far as I understand, that is your position, right? That ultimately dark matter doesn't explain everything that it needs to explain.
Exactly. So initially, 25 years ago, I had no issues with this. The hypothesis that there is dark matter is a sound physical hypothesis. It's a postulate, and then one can work with that. It can be put into equations, into the computer, and one can then do calculations of how heavenly bodies should be moving. And I've been doing that since, as I was saying, 25 years. And we've been testing this hypothesis, and it fails on every account we tested since. The very first calculations I did already showed me that there's something very fishy about this postulate. So, the postulate is correct, except that the observed universe just doesn't behave like that. And so we've been doing more and more tests, publishing research publications on this. And now I'm completely convinced. And in physics, we say we've reached well beyond the 5 sigma confidence limit that there is no dark matter. Dark matter absolutely does not exist. And I can maybe explain a very simple view of how one can visualize this test. Yes. If you imagine you have two sorts. You imagine you postulate there is a honey which is there, but you can't see it and you cannot feel it. So you've got a jar with this honey, and you put your hand in it, you wouldn't really feel it, and you can't see it, taste it, nothing. So you can put two jars next to each other. One is completely empty, and the other one has this fictitious honey in it, right? And you take a marble, two marbles, and you drop them down, and they fall down. Now, the one marble which goes through the glass, it's open at the top, it just falls down to the floor, just getting faster and faster, like an apple falling from a tree. The other marble, which goes into this jar, which has this invisible honey in it, will hit the honey, slow down, and slowly sink down, right? And then you know, okay, true, this honey is in there, just I cannot personally feel it, nor can I taste it. But I've made the experiments through this falling marble, so I know there is the substance in there. And that's basically exactly the type of tests we are doing with dark matter, because a galaxy has this dark matter halo around it. That's what the theory tells us. There's nothing you can do about it. That's a clear consequence of this dark matter theory. And so if you now take another galaxy and you drop it into this galaxy, and if it enters this dark matter halo, it actually slows down. The reason why it slows down, although it wants to fall towards the other galaxy, it's at the same time slowed down. And that's just like with the honey, it's just friction. And we call that Chandrasekhar dynamical friction, because Chandrasekhar developed this implication of this dynamics, I think the 1940s, if I'm not mistaken. Okay, so we've tested this, and the jar is empty. There's absolutely nothing there. So the galaxies pass each other, they're far too fast, which means it's not dark matter, it doesn't exist.
So Begin to Know asks, stellar velocities in galaxies cannot be predicted with dark matter. They can in MOND. That suggests that MOND is a better explanation, yet it is discarded by most. Explain, please.
Yeah, so imagine you want to go. So stellar velocities in galaxies cannot be predicted with dark matter. That statement is absolutely correct. Now, imagine you take a spaceship and you want to send it off to some other region of your galaxy. In the future, maybe this will be possible. The problem one would be faced with is if in the dark matter theory, you would know where to direct your ship, because there could be a dark matter clump on the left or on the right, and your ship would then be pulled to the dark matter. You'd have to steer against it using fuel, and you'd end up probably failing and dying of thirst and hunger, because you wouldn't have enough fuel with you to navigate. So it's unpredictable. If you have a observed galaxy, one cannot in the dark matter framework predict the way the stars are orbiting about the galaxy, because there's no way to say what sort of dark matter is there, how much dark matter there is. Okay, now in MOND, that is called modified Newtonian dynamics. Historically, I refer to it as Milgromian dynamics, because it was invented by Milgrom to be symmetrical with a Newtonian dynamics. So in Milgromian dynamics or MOND, one can predict the path of the ship precisely, because once you know where the matter is, just the stars and gas, you know exactly what the potential is. So you know exactly where to shoot your ship and how to navigate it without any margin of error, or basically very small margin of error. It's like in the solar system. We know where to shoot our ships because we understand the dynamics. The Newtonian gravity is perfectly valid in the solar system, and in the galaxy we do exactly the same, except you would have to use MOND instead of Newton. Now, why, given this situation, which is an interesting philosophical situation, because obviously a physicist would prefer the theory which can make precise predictions over the theory which absolutely cannot make predictions, and yet MOND is discarded. Yeah, and that's an interesting situation which goes into the realm of psychology and the history of science and philosophy of science. Something is happening in the community, the scientific community, which is very wrong. Very, very wrong. Yeah. So the taxpayer, and this makes me internally more unhappy, because as a scientist, one has the duty to towards the taxpayer who's funding us. We have the duty to do what we can to uncover the secrets of nature, so that our civilization can advance. Yeah. So just hypothetically, imagine we are actually starting to build an intergalactic civilization, and we need to know where to send our ships to the next stars and so on. And if scientists keep saying there is dark matter, then they would totally and massively mess up on a huge, fantastically huge scale. They would basically totally destroy this entire project, because there would be no way of knowing how to navigate your ship. I mean, this is a very serious situation. Why that is happening, I don't know. It's some instability which occurred where these people are quite bright, and I just don't understand how they so massively, on such a huge scale, actually go against Mond. I mean, we see this because we are now only working with Mond. In my research group, we don't touch dark matter anymore. At the best, we might write a paper on dark matter, because just to show yet another argument where it fails. Dark matter is no-go for us, absolutely, because it's just a total waste of time. Why does the neighbor next door still think very, very convincingly for themselves that there is dark matter? I really cannot understand. It is a grievous situation, and I think it's unique in history of science. It's never been like that before.
I think sometimes, we forget that, scientists are people too, and dogmatic thinking can
well, that's like saying, yeah, and I know that's often said as an excuse, but I don't accept that, because it's like saying the police are just people, and therefore we allow them to sometimes mess up their duties, right?
Oh no, I agree with you. It shouldn't be the case. Like, science should be held at a different standard, right? I mean, a lot of my channel is kind of examining religious beliefs and how people justify those claims, and my perspective is that ultimately they fail to do that. And it's very frustrating when something like science, which I hold up to the highest regard, sometimes can fall into those same patterns of dogmatic thinking, where these things just happen to be accepted, and it kind of becomes hard to break through those assumptions, even though it shouldn't be, because we should just be going where the evidence is.
I agree, of course. I mean, but the scientist is a different type of, so as a scientist, one is trained to follow logical principles, right, and look at the data and infer from the data and work towards a better understanding of nature. There's no room for personal belief. Doesn't exist in science.
Right.
Okay. So and I think the scientific system is totally failing at the moment, like massively.
And yeah, I mean, it's really unfortunate and surprising that something that is supposed to be kind of foolproof from keeping that from happening is failing so miserably.
Yes, well, I can tell you an example. For example, well, many will have heard of the Hubble tension. Don't know if you've heard of the Hubble tension, maybe. So yes. It would be in the media, maybe. It's a great discovery in a sense. So what one finds is that globally, the whole universe is expanding with a certain speed. Yeah, that's the Hubble flow. It's expanding from the Big Bang, and we know how fast the global expansion is, assuming the CMB is the remnant of the photosphere. You could say basically showing us the Big Bang happened. Then we know how the universe is expanding locally. If we measure the expansion rate using the local data, so in a small part of the universe around us, the universe locally seems to be expanding more rapidly. And these two don't fit together, but they should be, because the standard model of cosmology needs the universe to expand everywhere at the same rate. But what we observe locally is that the expansion rate is faster, significantly faster, because the errors are very small now, than the global expansion. And so this is now a big topic. There are conferences about this. A lot of the very, very important people are invited to give all these talks. And we've published a very simple solution to this problem, which is like completely, you could say, trivial. And the Hubble tension only exists because of using the wrong model, of course. Excuse me. And so what astronomers have discovered is that we live in a very underdense region. Okay, so if we can count galaxies outwards, to quite a large distance, out to hundreds of millions of parsecs, so nearly 500 million parsecs out, and we see that the number of galaxies per unit space, per unit volume increases. So locally we have an underdense region, and as we go and look further out, the density of matter increases, of galaxies increases. This is called the KBC void. It's seen in many different wavelength regions. If you look, you can see it also by counting galaxy clusters. We have a smaller number of galaxy clusters near us than in the further away universe. And what then happens is, if we are in such an underdensity, then the matter falls towards the sides which are overdense. It's like the apple falling to the ground. It's exactly the same effect. It's just gravitation working. So the galaxies are actually falling towards the sides of this underdensity. That's why it's an underdensity, because it's being emptied just because of gravitation. And the observer within this void, and we are within this void, then locally infers a fast expanding universe. Yeah, and we've shown the calculations. It's trivial. I mean, just exactly what, just taking the observed underdensity, you get this Hubble tension, and that solution is totally being ignored. I mean, it's basically what you get by observing the universe, but the great community out there prefers to continue making big conferences and discussing this Hubble tension in terms of physics in the dark sector, as we say, where one assumes that dark energy takes very complicated mathematical forms, or that there's a new era of dark energy appearing. Also, I mean, stuff which you can never ever measure or test in the laboratories. Esoteric physics, basically, what they are doing on a grand scale with a lot of money. And the very simple solution, which you get direct from observation, is just totally ignored. I mean, there's a big conference now in Corfu, for example, being organized. We are totally left out. There was a huge review on these tensions in cosmology published. This is not even mentioned in the review. And these are all the famous scientists who write these reviews. I honestly do not know what's happening there, but the cosmological community has basically gone bunks.
What do you think can be done to hopefully better this situation?
Well, that's a good question. I think it's so ruined that it's barely possible. Well, I think the only apart from firing everybody, that's the only possibility. That's not realistic. But the only way to do it is to actually let them be. Let them have, do what they would like to do, and provide funding for the groups who are actually looking at, the more correct picture. Because this is the other situation, that the research groups which are have broken away from the mainstream, the dark matter mainstream, so are now working with MOND, because with MOND we can actually do the computer simulation. There's no other theory we can use to do computer simulations of how galaxies form in a universe without dark matter, and that research direction is completely underfunded. I mean, it's basically impossible to get funding, because everybody says there's dark matter, and you just don't have a chance. And so the way to really move forward is to just let them be, let them do their work as they like, even though it's useless at this point, and add money into those areas which are actually investigating these new directions. That's the only realistic possibility. Of course, this will not happen because there's no money. So,
well, hopefully somehow we can get funding to the right places, right?
Well, that's difficult. I mean, even rich individuals who want to become immortal by founding institutes like Kavli and others, they still end up giving their huge donations to well-established research directions. So even there is no hope, I mean, little hope, actually.
One of the points of conversations that I've had recently with both philosophers and physicists is on this idea of falsification. Because for me, falsification seems to be how would I say this, a very important principle of doing science. And because of some of the philosophy of science that's taking place, some people seem to have kind of moved away from that being a central of an issue. But at that point, it seems like, what are you doing that's different than just, almost like religious speculation at that point, right?
I completely agree. I mean, this is extremely dangerous what's happening there for what we call the scientific method. I mean, if scientists start saying that falsification is not doesn't count anymore, then that is basically they would have totally lost their minds in terms of scientific, as being scientists, and it destroys totally the method. I mean, it's this thing, right? We have imagine Newton had invented the law of gravitation, which works just on Earth, and then we apply this to send spacecraft to Mars, but it fails. You shoot your spacecraft, and the spacecraft goes, to Jupiter, and then to Venus, whatever. It never goes to Mars, and there's always the same sort of deviation. And you would, so basically, you predict with your theory the trajectory, and that prediction would be wrong because the reality is actually pulling the spacecraft somewhere else. And you would stop using that law, right? You would try to find a better law of motion to stop wasting your billions because you're shooting the spacecraft in some other direction. And that's the principle of falsification. I mean, we have the principle of falsification because that allows us to sort out those mathematical constructions which can be very beautiful and impressive, but we have to not use those as physics, which just do not describe the real universe. And falsification is the procedure on how we do that, right?
Yeah. I think there's a difference between saying that there may be aspects to a theory. Like, we may not be able to falsify every single minute detail of a scientific theory, but that's a different thing than saying, well, in these contexts where we can actually perform experiments to show that these theories don't work, that we should just ignore the fact that they don't work. I think there's two different things. And sometimes I feel like people have taken the observation that we can't falsify every aspect of a theory and then taken that too far to kind of eventually undermine the entire process.
Well, yes, that's quite true. So I agree, sometimes you can't falsify the theory, but that's only because one can't do the corresponding measurements. If I can do a measurement, so the scientific principle works on, one develops a theory. It has to be mathematical because that's the only tool, a logical tool there is for this. That, if it's a good scientific theory, it will make predictions. Otherwise, it's not a theory which is of any use. And that prediction must be testable with experiment. And if one devises an experiment sufficiently accurate, so the uncertainties in the measurement are sufficiently small to show you that that prediction is wrong, and you reach the 5 sigma confidence limit, that's the standard. So you do it 2 million times, and you will always find in every single case that there's the prediction is not fulfilled with the measurement, then you lose trust in the theory and you discard the theory and you will seek a different formulation.
Begin to Know asks, have dark matter proponents realized they need to explain many things like the baryonic Tully-Fisher relation?
Yes. Now, this is an interesting point which David Merritt has been actually raised for the first time. I hadn't been aware of it so much myself. And that is that the textbooks on galactic astrophysics or galaxies, which students learn from, did not contain these type of laws. So the baryonic Tully-Fisher relation is an amazing discovery. It shows that it essentially means you observe a galaxy and you just measure how bright it is. And then you already know what's happening in this galaxy. I mean, basically, you know how fast the stars are moving, how big it is even. I mean, there's a different relation, mass-radius relation. And galaxies follow very well-defined laws. I mean, galaxies are an incredibly simple system. It's like stars. Yeah? So you look at a star, you know if it's a sun-type star, you know exactly how long it lives. You know at which time it will have which luminosity. And the same with galaxies. You see as a galaxy of a given mass, and you know what it's actually doing. And this Bernoulli-Fuchs relation tells us for a galaxy with a given luminosity, i.e. mass in stars and gas, you know how fast the stars will be moving and the gas will be moving around the galaxy. And that's a Bernoulli-Fuchs relation. There's basically no scatter on this relation. So within the measurement uncertainties, a one-to-one relation. And that is experimentally extremely well verified. And it has not been in the textbooks, because in the dark matter models, it doesn't work. Now, there are researchers who've written papers claiming that they can reproduce the Bernoulli-Fuchs relation. I mean, that is nonsense, because in dark matter theory, every galaxy has its own merger history, and you can never get this type of extremely well-defined relation in a theory in which galaxies form stochastic from various crashes between the galaxies. It's just physically totally impossible. They still claim that. This is grievous false reporting from our point of view. Furthermore, if they had been able, if their claim were true, then why did they not predict it? Because it's a fundamental relation of galaxies and has never been predicted by any dark matter modelist. They only post-predicted once the relation has been observed. Now, Magromian's gravity has made that prediction exactly when it was formulated in 1983, and it has been verified incredibly well. Now, a verification doesn't prove a theory. However, the point is that there has not been a single test which has been able to falsify MOND so far. Yeah, while every single test we are doing falsifies the dark matter theory. And I just want to repeat, I'm not against dark matter. It's a good and sound hypothesis, as I've been saying before. But as a scientist, that's just what we do. We test the hypothesis. That's a falsification principle. And dark matter theory fails every single test we've done. We've done many, many tests. We've reached well beyond the 5 sigma confidence limit. So then there are other relations, like the radial acceleration relation, which is where we look at the internal, how matter moves within the galaxy. So Bernoulli-Fuchs relation tells us what the speed of a whole galaxy is, basically the rotation speed. But the radial acceleration relation tells us the fine details within a galaxy. How does the matter move within a galaxy? The radial acceleration relation has been predicted in 1983 by the theory of Milgrom, and has been verified incredibly well. It has not been predicted by dark matter theory, and they can't get it to work in dark matter theory. And the observations are just amazingly showing how this RAR is functioning. And again, it has not been in any of the textbooks. So this is what David Madden, and he's published this point that the dark matter community has been basically suppressing this knowledge to make believe that it's not relevant. So when I speak to students, they are all completely amazed that these relations exist and that there are these problems.
But what do they think they're going to gain from, like, why are they doing this?
Well, this is what I was referring to before. This is a unique situation in history. We've never in history had so many highly educated scientists. I mean, many of these people come from Princeton, Harvard, MIT, and never in history have we had such a large number of extremely well-educated scientists who are so totally messing up. In the past, the discussion was between the few scientists which existed and the religious institutions, right? That's a totally different affair. I mean, it's not comparable to the catastrophe we have today. I mean, we are looking at a major failure of the whole system.
And what kind of criticisms have you received from these proponents of dark matter?
Well, there's been a lot of stress in the university. These people are very powerful because they get very powerful professorships with a lot of money, and so they can exert a lot of pressure, and this has been happening. I'm still in the middle of this. I mean, it's still not, I mean, we have big university-wide situations, you could say. It's potentially unpleasant. People look down upon you if you work on MONDs. They feel cleverer somehow, because they work on dark matter. Maybe it's related to the situation that they always feel close to Einstein, and so they feel clever. I don't know. It's difficult to understand how this instability has happened in the scientific system.
Especially when the evidence isn't on their side.
Well, the evidence is totally massively against the dark matter. Yeah.
It's really, the politics of academia is something that I find particularly repulsive. I mean, politics in general, but in a context where we're supposed to do better.
Well, exactly. I mean, this is what I was sort of referring to before. There's no excuse, right? I mean, the scientist is trained to follow the principle of falsification to advance our understanding of nature, and that's now massively failing now. It gets nasty because when you talk to these people, then, I mean, you see publications like just recently, the archive appeared a paper with a big title, Lambda CDM is alive and well, right? And this is after all the stress which has been happening with the Hubble tension and so on. Of course, they completely ignore what we've done on the Hubble tension, but they solve the problem. They argue, this is unbelievable. I mean, I get and I have to try to, it's not healthy to think about these things, but they claim in the scientific paper that the theory works extremely well because of unknown biases. Now, they're mentioning an unknown bias in the measuring the distances to Cepheids. Cepheids are a particular star which is in a evolutionary stage. It's a massive star. It might be 8-10 times more massive than the sun. So it's a blue star, and as it evolves, it starts to pulsate. That's just the internal way the photons interact with the matter, and the matter cools and raises temperature, so the apoicity is changed. So these stars pulsate, and they do so very, very regularly. And when they reach this instability, they have a particular luminosity, so we can use them as standard candles. So we measure the period, and we know how bright the star must be. Then we measure how bright it is on the sky, and we know how far it is. And this Cepheid distance measurement method has been excruciatingly well researched since 30, 40, 50 years. I mean, today people are looking at relativistic biases. So when the Cepheids are at sufficiently large distances, then the dilation, because of the redshift, changes the period. So you infer wrong luminosity, but this can be corrected for because one can measure the redshift. And then these people, they write that there are unknown biases in this Cepheid distance measurement, and that solves the problem. So basically, these people are arguing the theory doesn't fit to the data, and it doesn't fit to the data because the theory is correct, but that's because there are some unknown biases. Of course, you cannot predict anything because you don't know what your unknown biases are. And the next test with not Cepheids but something else would have again unknown biases, and you can't again predict anything.
I mean, that seems to be so counter science.
This is totally against science. So this is not the scientific principle, scientific method. It goes against my personal way of understanding science. I seriously dislike it. I don't know what to do about it because that's just currently what these people are doing, apparently.
Well, I'm glad that you're on to share, the stuff. So hopefully, I don't know. I'm trying to get education spread.
Well, we have to do something. I mean, our civilization has been extraordinarily successful. We've been able to go to the moon. We can theoretically go to Mars. I think technologically it is possible. That is the way to go. We can colonize the moon and do great, wonderful things. I mean, but the way this part of science has been evolving lately is a complete disaster. So we need to somehow save the system. I mean,
Adar asks, I thought the universe is the same everywhere.
Well, that's a good question. If in the Steinmar cosmology, which assumes there's this Big Bang, then the universe expands, we have dark matter, it has to be. That's the cosmological principle. It's a very reasonable hypothesis. I mean, it's something which you do when you do your calculations and you develop a model, then obviously you make such assumptions. It's like saying, let's first take a simple description of a cow and assume it's a spherical object. Like that's sort of what one does, because you can calculate it and then see where it deviates. And now the observations, of course, are showing us that it's not the same. So We don't have evidence that the laws of physics are different. They seem to be the same everywhere. So the atom here will be the same as the atom on the other side of the universe in terms of the electrons and the shell structures and energy levels. But the density of matter might vary. Now we know from this void in which we are, the KBC, the Keenan-Barger-Cowie void, which was published in 2012 and then verified with many other research papers, this huge underdensity already shows us that there are large-scale inhomogeneities which are massively incompatible with this simple model of a uniform, homogeneous, isotropic universe. Because this underdensity itself falsifies the model with more than a 6 sigma significance. So just measuring the distribution of galaxies around us kills the model already. Yeah, it's just wrong. And now this evidence there are differences in the density and that there are huge motions of matter on gigaparsec scales, which are totally incompatible with the standard model of cosmology. So it does look like the universe is much more structured, has much larger density contrasts on huge scales, and there's no theory for that at the moment. But we can infer this from measurements, and with MOND, what we know, we've done calculations with MOND, and we get these differences. Because in MOND there's effectively stronger gravitation, a simplified way you can say that, and actually it grows these density fluctuations to much larger extent than the Einsteinian gravity, and that's what we observe. And the KBC void is exactly such a case. It's perfectly consistent with the MOND cosmological theory, inconsistent with the Einsteinian model.
Begin to Know asks, please give us some insight in how to modify Einstein to get MOND in the appropriate regime.
Well, that's exactly what one cannot do. One cannot take Einstein and modify Einstein. One has to start, and that's what Milgrom did, from very simple principles and postulate, basically conjecture that once you reach a certain gradient in space-time, which is very small. So in the solar system, the gradient is quite big. We have pretty large gravitational effects, the sun, and then the whole galaxy is pulling at us. So we are orbiting around the galaxy. That's a fairly strong field regime where the curvature of space is still quite large. And that's when Newtonian gravity is valid. And he conjectured that if one now generalizes this and allows if one allows effectively the gravitational force to depend on the curvature differently to what Newton wrote down, so it gets effectively stronger when the curvature gets less. Effectively, it's not exactly what happens. Then one basically solves the whole problem. So it suggests. And this is, again, what Milgrom conjectured in a very interesting paper published 16 years after his first paper, that this may be related to what the quantum vacuum is doing. So in a non-curved quantum vacuum, the dynamics changes to this, what is referred to as space-time scale invariance. And that's a very simple symmetry somehow, which is not fully understood, but the equations of motion, so if a star is moving in that regime, it's different than in the regime where the sun is currently. And with that conjecture, one can develop an action, a Lagrangian, develop a generalized Poisson equation, and actually do fully self-consistent calculations, calculating the force field around any gravitating object in the vicinity of other gravitating objects, which is what we do in the computers these days, and get a very different type of a universe in the computer, which actually happens to agree with what we observe as far as the tests have been done. I mean, we haven't tested everything because there are maybe 3 people in the whole world who can do such calculations. And we have grave difficulties in keeping that funded, but we are doing what we can. It looks incredibly promising, I must say.
Yeah, in fact, the next questions that were asked was, do you have people working on your ideas, and is your work funded?
Well, we are working on the ideas of Milgrom, Morty Milgrom, who formulated this theory with Bekenstein. So 1984, Bekenstein and Milgrom wrote another very, very influential paper, which actually gave us the equations which we are now using. And yes, we have a team in Bonn, in Prague, in St. Andrews. There are one or two people in Strasbourg. So in Case Western University, United States, actually is a very strong, Stacy McGough is very prominent. But the way we are funding it in Bonn and Prague is through institutional money, which I managed to organize. Getting grants on this NSF, say, in the United States would be entirely impossible because you just don't have a chance. In fact, I once had an offer to go for a professorship in the United States, and I declined that because I already foresaw these situations that here, even though it's difficult, we can still do research funded through the institution because there are other clever people around to understand that maybe we should try these other approaches, and then we get a little bit of money. In the United States, it would be entirely impossible, because I would be damaged. If I were a professor in the United States, I would be damaging the institution simply because I wouldn't be getting grant money.
Wow.
Yeah, and that's of course a problem. So here in Europe, in that sense, it's actually better, much more advanced in that sense. We are freer to do the type of research we feel is important. We need that freedom.
This actually hits to a point I was just about to make. Newton is a god. Milgrom has not been canonized. Therefore, Mon cannot replace F equals ma. Is religion deeply ingrained in us?
Yeah, that's a good way to summarize the situation. Yeah, I think that's probably maybe a way of putting it. It seems to be religious. I mean, even some theoretical physicists here, I've seen their research papers they've written. I mean, they make statements like "dark matter exists!" exclamation mark, and I've then emailed to them that this is actually unscientific because you can't make that statement as a scientist. Yes, there's an extremely strong religious belief in dark matter that is actually true, and I do not understand where that comes from. Maybe it's some tribal behavior where young people feel better psychologically if they can associate themselves with a bigger group, a bigger tribe, more powerful tribe, the tribe which has more money, more resources, and that's of course these days the dark matter groups, right, or dark energy groups, and if a student would have to be very, very intelligent and very, very interested in truly understanding the secrets of nature to join a group which is underfunded and looked down upon by the others. I mean, one really has to have a very strong character to go into that direction. Right. I think, and usually, well, the way we start is that we have students coming in, and then often they're underfunded until one can organize some better funding.
Arbor asks, do you only work on falsifying dark matter, or what work first turned you away from the dark side? Well,
I don't only work, I mean, most of my research is actually on stellar populations. That's how I did my PhD, and we are still continuing. I've developed a method of the IGMF theory, as it's called, how we can calculate what a galaxy looks like at the edge of the universe just from the physical the conditions, their density and metallicity. So that's actually a major part of the research here of the group and myself. We look at star cluster dynamics. That's another major area of how do stars form in clusters, how do they disperse into the galaxy, binary stars, planetary systems, how do they form? We've had quite a lot of research on that. So dark matter, I sort of touched upon. It's not, well, it's now becoming an increasingly important part of my research because it is simply the most important question we have, right? And as I've said before, I've convinced, we've done rigorous logical tests. Does dark matter exist? The tests have all been very negative at more than 5 sigma confidence. So I'm now, as a scientist, completely convinced there is no dark matter. And if there's no dark matter, and if I want to understand how galaxies work, I need to go to a theory which allows me to do that. And that is then Milgromian gravitation. So we are now testing Milgromian gravitation. just like we tested the dark matter theory, we are now testing Milgromian gravitation, which means we need to do a calculation of how galaxies form, and then we want to compare these galaxies in the computer with the observed galaxies and maybe see if we can falsify the theory. So far, as I was saying, it has been completely impossible. The theory is incredibly successful. I mean, every prediction made in 1983 has been verified. So there's been no disagreement with data, which doesn't mean the theory is true. You can never prove a theory, but you can keep testing it. And so far, all the tests have been positive. And so we are now working on Milgromian gravitation simply because it's the successful theory. It's only the only theory we can use in the computer to do such calculations.
Begin to Know asks, falsify for us the following statement. The relatively low second peak of the CMB power spectrum is compelling evidence for dark matter. Well, first, if you can explain what any of that means, because I don't know what.
Well, I mean, this is touching the CMB now, and I have never really done much research on that. I'm sort of starting to get into that, but so these are the acoustic peaks, right? So the basic density waves, which I mean, when the universe was born, according to the current understanding, they were sound waves propagating through this plasma, which was cooling because the universe was expanding, and at some point they froze out. And when they froze out, they sort of gave a characteristic dimension that's measured with a different the separation of the peaks, if I recollect this correctly, and the amplitude of these peaks. So the amount of power you have in which scale, which relates to having extra matter which gravitates, because that damps these. So the baryons, the hot gas, wants to go in sound wave, but the dark matter doesn't follow that because it's not interacting with the matter normally. It only interacts gravitationally, so it stays behind, pulls the baryons back, and this reduces the fluctuations. I mean, this is a broad type of description, if I recollect this correctly right now. And so by measuring these different heights, you can actually get an understanding of the amount of gravitating matter you need to have, as well as the geometry of the universe. And yes, in that framework, the height of these peaks tells us there must be additional non-gravitating additional gravitating matter, even in a Mond cosmology, right? So if we now say there is no cold or warm dark matter, then we need to use Milgromian gravity. But if we do a cosmological model in Milgram gravity, we still have to fit this power spectrum, and then one actually gets it all correct, except that this peak is not quite, if I remember correctly, it's not high enough. So in order to bump it up, one has to add a certain gravitating component, which has been identified as probably being sterile neutrinos. Now, that is a relativistic form of dark matter. It's like neutrinos, except it's sterile, so it doesn't interact. Well, I'm starting to be a bit... my knowledge is starting to slip here, so the neutrinos change their flavor as they propagate. In order to conserve energy and momentum, you need to postulate a fourth particle, which would be the sterile neutrino, and that's very difficult to detect. That sterile neutrino comes from neutrino physics. It's not proven. It's one possibility to explain these neutrino oscillations. And that sterile neutrino would play the role of this hot dark matter component, as it's called in a Mondian cosmology. It's a very different form of dark matter. It's not as exotic as the cold dark matter. It's actually related to the standard model of particle physics in a more natural way through the neutrino physics. Nevertheless, so this is just one possible interpretation, taking the CMB to be the photosphere of the Big Bang. Now, is that true? That's the other situation, so another question. Now, it's entirely possible, and this goes back to the ideas of Fred Hoyle, actually, many, many years ago, and these have been revived recently by Václav Wawrzyk in Prague, who's written a research paper pointing out that there is dust between the galaxies. Okay, so because this is measured, you look at quasars, you see that there is matter between the galaxies, which is, and you get actually some reddening and absorb, like the reddening basically. And so one knows that there's dust between galaxies. This dust radiates, and if you go backwards in time, the universe was smaller, and this density of this ancient dust between the galaxies, who knows how it got there, right? But there's dust between galaxies, and this density of dust was higher at the time the universe was overall warmer. There was more young stars, they were all closer together. And if you now calculate the radiation of this dust, because dust absorbs visible light and re-radiates this in the infrared at some 200 micrometers. And then this radiation, if it's redshifted, because it comes from a very young universe, which would have been very dusty, just taking the dust between the galaxies today, go backwards in time, you know the universe would have been very dusty, the very early universe. That flux of photons seems to correspond to the CMB. This is what Favriciuk has published and calculated. And now, if that is correct, so since I've seen that paper that was published in 2018, I went around, asked observers, is this dust really there between the galaxies? Everybody is confirmed it's there. And this, of course, would be a nuclear bomb for cosmology, because it would mean that the CMB would be dust emission and would not be the photosphere of the hot Big Bang, which means if that is the interpretation of the CMB, which is today completely not favored. I mean, every CMB expert would think I'm an idiot just mentioning this. Yeah? Nevertheless, the paper has been published, the dust is there, dust radiates, and so those photons have to be accounted for. You have to subtract the dust photons from the CMB, and according to Wawrzyuk's calculation, there's nothing left. In that interpretation, the CMB would be dust emission from the early universe, mostly from the early universe. In that interpretation, you would have to use this boundary condition. So the fact that the universe is radiating as the CMB in a very, very, very different way. It would not be the photosphere of the hot Big Bang. The acoustic peaks would be, the peaks in the power spectrum would have a different meaning, and we'd have to completely reinterpret this.
So, taking a slight different, how do I say this? A little bit off topic, but it's something that it's like an ongoing conversation on this channel. How do you respond to those who claim that science, or to do science, you have to make certain presuppositions? Like, we are presupposing that logic somehow corresponds to reality, or we are presupposing induction, or we are presupposing certain axioms like simplicity when we do science. And in that sense, you know, usually when I see people make these kind of claims, they're trying to make it seem like religion and science are closer together as far as using some kind of faith in these tools. I think that's the wrong move to make, but I'm always curious to see how people in the actual field look at presuppositions.
Well, I think this is a really fascinating question. Obviously, our theory of the way the universe works comes out of our minds, right? So it sort of reflects our, you know, it also shows the limitations of our minds, of course. Nevertheless, for me, when I look at the universe, we're trying to understand how these things work, it is entirely and totally non-religious. It has the question of whether there's some sort of higher being plays absolutely no role, not in my thinking at all. I'm not at all influenced by that. And I'm very pragmatic. What I want to know is if I have an equation which tells me how the matter reacts to gravitation, and I want to know, is this equation correct? And then if it's so far been testing and is shown to be correct, so that's now Milgromian, the Milgromian equation, then of course the questions arises, where does it come from? Yeah? And what is the deeper theory which includes this equation? And that, of course, there are experts in Prague, Skordis and Zloznik, who've been doing this. They've been trying to find out how Milgramian gravitation can come from a relativistic formulation, like what Einstein did, except for this is more complicated because we are looking at a more involved theory of gravitation. And that's all just essentially boils down to pure mathematics in the end. Yeah? But then the question is that fulfilling? I mean, you've got very complicated equations. Well, it's still a nice form, right? It's just a little bit more rich. It's richer. You could say it's not more complicated, richer in its physics, in its mathematics. And then the question is, does that satisfy me? I mean, what do I feel from that in a sense of deeper understanding? Yeah? And that's an interesting question. Do we find limits? You know, and that's something which we don't usually discuss much because there's no end to that, and we wouldn't be able to do calculations or send spacecraft anywhere. You know?
I mean, something I'm fascinated by is trying to figure out, is there a way to translate mathematics into a language that we can all understand?
No.
Which is concerning, you know, for someone who's in the philosophy perspective, that is a problem.
It's sure. I mean, I've been in PhD exams in mathematics. So in the way it works here is that if there's a PhD exam coming up for somebody saying mathematics, then two people have to be from the close field. So one has to be the supervisor, the other one has to be related to that mathematics. Then another one has to be from a field which is still related, so in that case it would be physics, and then somebody has to be from a field which is entirely unrelated but still natural faculty of science, so it would be like a biologist or something like that. So which means I've been seeing PhD exams in pure mathematics, and there's no way of communication. You just can't do it. I mean, they communicate through axioms, theorems, logical proofs in spaces you cannot even imagine. They can't imagine it, but they have the formalism, so they can do these calculations. But there's no way to put this into any form of language. I mean, they have to invent terms which somehow relate to, like, you know, there would be some sort of green transposition. And then I would ask, so what is the green transposition? Can I visualize something about it? No, it's just a term given to a set of rules which operate on some higher dimensional space constructed, you know, as a subset of some other more, you know, higher dimensional space or something. I mean, there's no way of being able to communicate. Yeah. Physics is actually the only way, I think, where mathematics communicates with reality.
Physics, okay. Yeah, these are definitely interesting questions. I think kind of my response to the theist talking about science making presuppositions is that I think that, you know, if I want to see if a pen works, I test to see if the pen works. Yeah. I don't think I'm presupposing anything there. A presupposition is something I can do only after I already have the tools of rationality. And that, I think, probably arises out of a combination of it being partially innate and then just my experience of the world being in the world. And I can doubt that God exists. I can't doubt the tools of logic in the same way, because that would be contradictory. So I think, to me, there seems to be a difference there.
That's a very good point, actually. That's a nice way of putting it. You can doubt the existence of God, but you can't doubt logics.
And ultimately, even if those tools somehow don't actually correspond to reality the way we think they do, we have no other way of navigating that. Like we can only do our best with what we have.
Well, I'm sort of thinking that logics is an inherent part of reality, because reality always has to be causal. You can't get something from nothing, right? And that's which means if anything happens, it's always a consequence of something else, and that's just pure logic. So the world always has to be logical, just because they are conserved quantities, which maybe then is a question, what about quantum mechanics? But maybe that's just a mathematical description of a deeper reality, which is not actually just like random and stochastic.
There is some interesting work both in philosophy and physics that look at causality a little bit differently. Like there's a difference between a cause and an explanation. And that's something that I've learned doing this show for a while is that the people in this field seem to be making a distinction there. I would love to have you again on the show at some point with Dr. David to talk about causality, because he's been on the show. He's a regular on the show, and we've talked about whether or not causality is like a fundamental or an emergent feature. And yeah, I'm always trying to. I would love to have you back. I think I really appreciate your time. Guys, if you have any last questions, we're just hit the 106 mark. Usually we do an hour and 20 minutes. If you guys have any last questions, feel free. Thank you, Dr. Kroupa. It's been a real pleasure.
Well, thank you.
And I think, here's one question that I missed. Do you have to be really courageous or really intelligent to go against everyone as you do?
Well, you could maybe say one has to be particularly stupid to do that. I don't know. I mean, I want to know how nature works. I mean, that's why I'm doing science. I mean, I went into the PhD simply because of that. And if the colleagues, I mean, if the majority go in a different direction, then I think it's correct. Then I just go into a different direction, right? And that's just what happens. Of course, you need a particular character probably to do this, maybe even forcefully. That's true. That's sort of the referring to being stupid. I mean, if I were particularly keen on always balanced and really being very careful not to upset anybody, then I wouldn't be doing this particular interview, I think.
Yeah, I think the people that have usually led to change are those that are not afraid to challenge the status quo, and kind of stand up for what they think is right. So I definitely appreciate your time here and sharing with us how you understand things to be. I'd love to have you back at some point, discuss these things further. Guys, as always, thank you for joining us. If you want to support the channel, like, subscribe, patreon.com/AxiomsOnTrial. Again, if you have any questions that you want our guests to answer in the future, always feel free to email us, axiomsontrial@gmail.com. Yes, I agree with her. Indeed, he and Begin to Know should totally get on together. I love that conversation. I think that would be a really great episode to have on the channel. So, thanks again for coming on, and thank you guys for joining us. The next show will probably be in a few days. I'll keep you guys posted. I'm not sure the details yet, but we'll definitely be coming back soon. I'm trying to get more content out there on a regular basis. So thanks again, and I will see you guys again soon. Thank you, Doctor. Thank you so much.
Nice to meet you.
Nice to meet you as well. Thanks.